Yes, we are going to start 11.3. Give me a minute. Eleven point three deals with the integral test. Let f be a continuous positive and decreasing function, and let an is equal to f of n. See the difference between x and n. N is a natural number, x is any real number. So f be a continuous positive decreasing function and an is equal to fn. Then if integral 1 to infinity fx dx is convergent, then sigma 1 to infinity, n varies from 1 to infinity, an is convergent. So if the integral is convergent, then the series is convergent. If integral 1 to infinity f prime x dx is divergent, then sigma n varies from 1 to infinity, an is divergent. So see the difference between these two. And then there is a test called the p-test. You have seen this p-test in the integral, that section. So here is a p-test. Sigma n varies from 1 to infinity. 1 over n to the p is convergent if p is greater than 1, and is divergent if p is less than or equal to 1. Rn is equal to an plus 1 plus an plus 2 plus an plus 3 plus etc. is the remainder after n terms. Remainder after the first n terms. So integral n plus 1 to infinity fx dx less than or equal to Rn less than or equal to integral n to infinity fx dx. So that's a relationship between remainder after n terms and the integral. So if you add Sn on all the three sides, you get Sn plus integral n plus 1 to infinity fx dx less than or equal to Rn plus S, that is, sorry, Sn plus Rn, that is S, less than or equal to Sn plus integral n to infinity fx dx. And in general, sigma 1 to infinity an is not equal to integral 1 to infinity fx dx. That integral test is used only to check whether it is convergent or divergent, but you cannot estimate, you cannot find the value by integration. The actual value may be estimated by the average of the left side and the right side on equation number 1. So if you find the average of these two, the first expression and the second expression, then that is a good estimate of yes. Error in the estimate is at the most 1/2 of the interval in 1. So the interval in 1, you have to find that interval and then divide that interval into 2. Okay, here is the question from the textbook. The question is, use the integral test to determine whether the series is convergent or divergent. Number 4, sigma n varies from 1 to infinity n to the power of negative 0.3. So let fx is equal to x to the power of negative 0.3. See, an is equal to n to the power of negative 0.3. So fx is, you replace n by x, fx is x to the power of negative 0.3. Now you evaluate the integral from 1 to infinity fx dx is equal to integral 1 to infinity x to the power of negative 0.3 dx. Apply the power rule, x to the power of negative 0.3 plus 1 over negative 0.3 plus 1. That is x to the power of 0.7 over 0.7 from 1 to infinity. That is 1 over 0.7 times infinity to the power of 0.7 minus 1 to the power of 0.7. Infinity to the power of any positive number is infinity. So this is infinity. Since it is infinity, the integral is divergent. Therefore, the series is divergent. Number 6. Sigma 1 to infinity. N varies from 1 to infinity. 1 over 3n minus 1 whole to the power of 4. Therefore, fx is equal to 1 over 3x minus 1 whole to the power of 4, because you replace n by x. Therefore, integral 1 to infinity fx dx is equal to integral 1 to infinity 3x minus 1 whole to the negative 4, because fx is 1 over 3x minus 1 to the 4, means that is 3x minus 1 to the power of negative 4. That is equal to 3x minus 1 whole to the negative 3 over negative 3 power rule. Multiply that by a 1 over 3, because the coefficient of x is 3. Now substitute the limit negative 1 over 9 times 1 over 3x minus 1, the whole cubed, from 1 to infinity. That is negative 1 over 9 times 1 over infinity, that is 0, minus 1 over 2 cubed, when x is equal to 1. 3 times 1 minus 1, which is 2 cubed. So that is equal to 1 over, this is 8. 8 times 9 is 72. So that is positive 1 over 72. Therefore, it is a finite number. Therefore, integral 1 to infinity fx dx is convergent, and therefore integral 1 to infinity 1 over 3n minus 1 whole to the 4 is convergent. Number 8. Integral 1 to infinity n square e to the negative n cubed. So let fx is equal to x square e to the negative x cubed. So integral 1 to infinity fx dx is equal to integral 1 to infinity x square times e to the negative x cubed dx. You substitute u is equal to x cubed. So du is equal to 3x square. Du over dx is 3x square. So x square dx is equal to 1/3 du. So that integral is equal to integral x varies from 1 to infinity e to the negative u times du over 3, because x square dx is 1/3 du. That is 1/3 times e to the negative u over negative 1. X varies from 1 to infinity. You replace your u. U is x cubed. So that is negative 1/3. 1/3 times, well, there is a negative 1. So negative 1/3 e to the negative x cubed. X varies from 1 to infinity. That is negative 1/3 times e to the negative infinity minus e to the negative 1. E to the negative infinity is 0. So negative 1/3 times 1 over negative 1 over e. So that is 1 over 3e, which is finite. Therefore, integral 1 to infinity fx dx is convergent, and therefore the corresponding series sigma n varies from 1 to infinity n square e to the negative n cubed is convergent. Number 12. 1 over 5 plus 1 over 7 plus 1 over 9 plus 1 over 11 plus etc. This is the denominators are in arithmetic progression, arithmetic series. So nth term is 1 over 2n plus 3. You just substitute n is equal to 1. You get 2 times 1, 2 plus 3, that is 1 over 5. When n is equal to 2, 2 2s are 4, 4 plus 3 is 7. So you get the second term. When n is equal to 3, 2 3s are 6, 6 plus 3 is 9. You get the third term, and so on. So an is 1 over 2n plus 3. Therefore, fx is 1 over 2x plus 3. Therefore, integral 1 to infinity fx dx is equal to integral 1 to infinity 1 over 2x plus 3 dx. That is equal to natural log of 2x plus 3 divided by 2. It's not a 3. This must be a 2. That is a mistake on my part. That is, you have to correct that mistake. So this is a 1 over 2. So this also is a 1 over 2. 1 over 2 times natural log of infinity minus 5, which is infinity. So the integral is divergent. Therefore, the series 1 to infinity 1 over 2n plus 3 is divergent. Please correct this mistake. The coefficient of x is 2. So that 2 must come here, not the 3. Number 14. 1 plus 1 over 2 square root of 2 plus 1 over 3 square root of 3 plus etc. So n is equal to 1 over n times square root of n. Second time 2 square root of 2. Third time 3 square root of 2, 3. Fourth time 4 square root of 4, etc. So nth time is 1 over n square root of n. So fx is x times square root 1 over x times square root of x. Integral 1 to infinity fx dx is integral 1 to infinity x to the negative 3 half. 1 plus 1 half is 3 half. Negative 3 half dx. So integrate that. This is x to the negative 1 half over 1 half. Power rule. X varies from 1 to infinity. That is negative 2 over square root of x. From 1 to infinity, that is negative 2 times 1 over infinity minus 1. Negative 2 times 1 over infinity minus 1. 1 over infinity is 0. So the answer is 2. So it is finite, and therefore integral fx dx converges, and therefore integral sigma 1 to infinity 1 over n square root of n is convergent. And here you may use the p-test also, because 1 over n to the 3 half, p is greater than 1. So by p-test, it is convergent. Number 16. This is integral 1 to infinity is square root of n divided by 1 plus n to the power of 3 half. So we are going to use the comparison test here. So 1 plus n to the power of 3 half is less than or equal to 2 times n to the power of 3 half, because 1 is less than or equal to n to the power of 3 half. And so 1 over 1 plus n to the 3 half is greater than or equal to 1 over 2 times n to the power of 3 half. Therefore, square root of n divided by 1 plus n to the power of 3 half is greater than or equal to square root of n divided by 2 times n to the 3 half. That is square root of n over 1 plus n to the 3 half is greater than or equal to 1 over 2n, because 3 half minus 1 half is 1. 1 over 2n, and that means sigma 1 to infinity square root of n over 1 plus n to the 3 half is greater than or equal to integral 1 to infinity 1 over 2n. That is, by p-test, right side is divergent. Therefore, the left side is divergent. In this case, you may use the integral test, but integral test is slightly difficult because you have to integrate square root of x divided by 1 plus x square root of x. It is integrable, but this is more easy. And in the next section, you learn limit comparison test. This problem is more appropriate there. We will discuss it in the next section. Number 18. 1 sigma 1 to infinity 1 over n square plus 2n plus 1. So you better graph it and see how the graph looks like. 1 over x square plus y is equal to, clear, 1 over x square plus 2x plus 2. Let us change the window, because it cannot be negative, it's integers. So window 0 to 10, negative 1 to 1 will be fine. So see that graph. So from that graph, you see that fx is continuous, positive, because it is above the y-axis, x-axis. So it is continuous and positive and decreasing. Therefore, you can apply the integral test. Integral fx is equal to 1 over x square plus 2x plus 2. So, integral 1 to infinity fx dx is equal to integral 1 to infinity 1 over x square plus 2x plus 2. That is written as x square plus 2x plus 1 because x square plus 2x plus 1 is a perfect square. So that is integral 1 to infinity 1 over x plus 1 the whole square plus 1 square. This is tan inverse x plus 1. Integral of 1 over 1 plus x square is tan inverse x, and so this is tan inverse x plus 1 from 1 to infinity. So that is tan inverse infinity minus tan inverse 2. When you substitute this, tan inverse infinity is pi over 2. So pi over 2 minus tan inverse 2, that is finite. Therefore, integral 1 to infinity fx dx is convergent. Therefore, integral 1 to infinity 1 over n square plus 2n plus 2 is convergent. And here again, the comparison test will work. N square plus 2n plus 2 is greater than n square. Therefore, 1 over n square plus 2n plus 2 is less than sigma 1 over n square. Right side is convergent because of the p-test. And so the left side is convergent. So that's another way. Here, if I ask you to show that by using the integral test, then you have to do this. Otherwise, you can use the comparison test. Number 20. Sigma n varies from 3 to infinity, 3n minus 4 divided by n square minus 2n. And so fx is equal to 3x minus 4 divided by x square minus 2x. You draw the graph from 3 to infinity, and then you will see that it is continuous, positive, and decreasing because it is above the xy plane. If you want, you can show you the graph. This is 3x minus 4, y is equal to 3x minus 4 parenthesis 3x minus 4 divided by x square minus 2x. You set the window from 3 to infinity, 3 to 10 or 3 to 20, whatever it is. 3 to 20. See the graph. So it is decreasing, positive, and continuous. So from the graph, it is clear that fx is continuous, positive, and decreasing. So you can use the integral test. Let us decompose it into partial fractions. 3x minus 4 divided by x square minus 2x is 3x minus 4 divided by x times x minus 2, that is a over x plus b over x minus 2. Multiply by the LCD, you get 3x minus 4 is equal to a times x minus 2 plus b times x, that is ax minus 2a plus bx, that is a plus b times x minus 2a. So a plus b is equal to 3 and minus 2a is equal to negative 4. Therefore, a is 2 and b is 1. So integral 3 to infinity 3x minus 4 divided by x square minus 2x dx is equal to integral 3 to infinity 2 over x dx plus integral 2 to infinity 1 over x minus 2 dx, that is 2 times natural log of x plus natural log of x minus 2, and this is 2 times natural log of infinity plus natural log of infinity upper limit, so it is infinity. Integral is divergent because it's infinity. Therefore, integral 3 to infinity 3n minus 4 divided by n square minus 2n is divergent. Number 22. Integral 2 to infinity natural log of n divided by n square. Here again, you draw the graph and see that it is continuous, decreasing, and positive in the interval 2 to infinity. So, integral 2 to infinity fx dx is equal to integral 2 to infinity natural log of x divided by x square dx. That's a good integral. Let x is equal to e to the u. So, 1 over x is e to the negative u. Dx is e to the u d. X is e to the u. So, dx is e to the u du. E to the negative u is the same as 1 over x. So, integral 2 to infinity u times e to the u du divided by e to the u the whole square. So, that is x square is e to the u the whole square. And so, that is 2 to infinity u times e to the negative u. One of the e to the u's cancel, so e to the negative u, e to the negative u. Now, you have to use the integration by parts. First function u, second function 1. Second function e to the negative u, and then you differentiate u, derivative is 1, derivative of 1 is 0, and the derivative of e to the negative u is negative e to the negative u, and the derivative of negative e to the negative u is e to the negative u. Change the middle sign and multiply, so that is negative u e to the negative u minus e to the negative u. X varies from 2 to infinity, that is negative natural log of x over x. E to the negative u is 1 over x. So that's the reason why I calculated it. So natural log of x, negative natural log of x divided by x minus e to the negative u is 1 over x. Substitute the limit, you get natural log of infinity over infinity, that is a 0. You may use the L'Hopital's rule there. I think I have skipped that part. It is actually a 0 because you use the L'Hopital's rule here, natural log of x over x. Second one is 1 over infinity, so that part is 0 minus negative natural log of 2 over 2 minus 1 half, that is natural log of 2 plus 1 all divided by 2, which is finite. Therefore, the integral is convergent. Therefore, integral 2 to infinity natural log of n divided by n square is convergent. Number 26. Sigma 1 to infinity n over n to the 4 plus 1. N to the 4 plus 1 is greater than n to the 4. Therefore, 1 over n to the 4 plus 1 is less than 1 over n to the 4. Therefore, n divided by n to the 4 plus 1 is less than n over n to the 4. It is n over n to the 4. That is, actually it is 1 over n cubed. So this is 1 over n cubed. N divided by n to the 4 plus 1 is less than n divided by n to the 4, which is 1 over n cubed. This n is a 1. And so sigma 1 to infinity n over n to the 4 plus 1 is less than sigma 1 to infinity 1 over n cubed. Right side is convergent because of the p-test. Therefore, left hand side is convergent. So instead of using the integral test, we applied the comparison test. As I mentioned earlier, in the next section, you will see a more easy way, which is known by the name limit comparison test. This is the comparison test. Next section is limit comparison test, which is more efficient than the other methods. Okay, now the question is here. Explain why the integral test cannot be used to determine whether 1 to infinity cos square n divided by 1 plus n square. 1 plus n square is convergent. So fx is cos square x divided by 1 plus x square is a decreasing function. So you see the graph is not a decreasing function. Let us draw the graph. cos square x y is equal to cos square x means cos x the whole square divided by 1 plus x square. So let us set the window. See, it is not a decreasing function. It decreases, then again increases, then again decreases, and so on. So this is not a decreasing function in the interval 1 to infinity, and therefore you cannot apply integral test for this. Then find the value of p for which the series is convergent. That also is not a very easy question. So fx is 1 over x times log natural log of x times natural log of x all to the power of p. And integral 3 to infinity, here the limit is from 3 to infinity. 3 to infinity fx dx is integral x varies from 3 to infinity 1 over x natural log of x times natural log of x. Let u is equal to natural log of x. So du is equal to 1 over x times natural log of x. So 1 over natural log of x times 1 over x. So that is 1 over x times natural log of x dx. So this is integral 3 to infinity du over u to the p, and that is u to the negative p du. So u to the 1 minus p over 1 minus p, because power rule, u to the negative p plus 1 over negative p plus 1. So substitute the limit from 0 to from 3 to infinity. I did a mistake here. So 3 to infinity, this is natural log of, this is 1 minus p. It's not 1 minus p, it is infinity. So when you substitute the upper limit, you get natural log of infinity divided by 1 minus p. And so this is finite if 1 minus p is negative, that is 1 is less than p, or p is greater than 1. You don't have, this is a long way, you don't have to go by the long way. You can stop here itself. Because of the p test, if p is less than 1, this is divergent, and if p is greater than 1, it is convergent. So you may stop here. Integral 3 to infinity du over u to the p is convergent if p is greater than 1, and divergent if it is less than or equal to 1. P test. So discard the remaining part. You can stop here. Number 34. Given that sigma 1 to infinity 1 over n square is equal to pi over 6. So this means 1 over 1 square plus 1 over 2 square plus 1 over 3 square plus 1 over 4 square plus etc. is pi square over 6. A part of the question. Find 2 to infinity 1 over n square. So 2 to infinity is 1 over 2 square plus 1 over 3 square plus etc. That is equal to 1 over 1 square plus 1 over 3 square etc. minus 1 over 1 square, because there is an additional term. So if you call this as s, then it is, this one is s minus 1 over 1 square. So it is pi over 6 minus 1. That is pi over 6 minus 1. Next, b part. Sigma 3 to infinity 1 over n plus 1 the whole square. So n plus 1 is 3 plus 1, 4 square plus 5 square plus 6 square. So you look at the series, 4 square plus 5 square plus 6 square. That is from this part. So you have to subtract 1 over 1 square plus 1 over 2 square plus 1 over 3 square from pi over 6. So this is, you subtract the first 3 times, then you get it. So sigma 1 to infinity 1 over n square minus 49 over 36, you see whether that calculation is right. One over 1 square, that is 1, plus 1 over 4 plus 1 over 9. Math, fraction. 49 over 36. So you have to subtract the first three terms from that infinite series. So it is pi square over 6 minus 49 over 36. 2 sigma 1 to infinity 2n 1 over 2n the whole square, that is 1 over 4 n square. So that is 1 over 4 times sigma 1 to infinity 1 over n square, which is 1 over 4 times pi square over 6. Answer is pi square over 24. Number 38, the last question. Here the question is, find the sum 1 to infinity n e to the negative 2n correct to 4 decimal places. We know that Rn is less than or equal to integral n to infinity x e to the negative 2x dx. So you calculate that this is n to infinity. Integration by parts. First function x, derivative is 1, its derivative is 0. Second function e to the negative 2x. And the derivative is e to the negative 2x over negative 2. Its antiderivative is e to the negative 2x over 4. And change the middle sign. You get x negative. There is a negative 2 in the denominator. So negative x e to the negative 2x over 2 minus 1/4 times e to the negative 2x divided by 4 from n to infinity. So this is e to the negative 2n pulled out times 2n plus 1 divided by 4. This is the remainder after n terms. And that must be less than or equal to 0.0005 because 4 decimal place means the remainder after n terms must be less than or equal to 0.0005. Now use a calculator. N is equal to 5. You get n is equal to 5. See, when n is equal to 5, this expression is 5.5. The expression is less than or equal to 0.05. And so n is 5.5, that is approximately 6. Now you have to find the S5 is enough. So if n is equal to 5.5 or 6, remainder is less than 0.0005, and therefore S5 is the most appropriate answer. So add first 5 terms of this series. You use the calculator, add first 5 terms, and then you get 0.1808. This is correct to 4 places, rounded to 4 places of decimals, because remainder after n terms is evaluated by using the integral test. Okay, so that is the end of that section.